Jasmin Blanchette and Mitrai Treitel. I don't know how to pronounce. So I'll let you the microphone.
Okay. We'll have to wait for Andre because he's going to start it. Are you there?
Welcome to our talk.
Okay.
It is joint work with Jasmin and Dimitri, our long-term collaborators. Let me very quickly say what we do in this paper, because I may not get a chance to during the talk. We introduce a general framework that makes it easy to reason about possibly complex variable bindings. It emphasizes modularity, and it is more flexible than nominal logic, say, in that it deals with infinitary structures as well, such as co-data types. The framework has been formalized in Isabelle Hall and will be made available as a definitional package. It will be made available to the users soon. In this talk, we're going to focus on the main question that has triggered this work. So, Lorenzo, what is a binder? Lorenzo's PhD defense is in 2 weeks, by the way.
So I've looked up the literature and I found many expressive formats which allow to specify fairly sophisticated bindings.
Hold on. Before going into those, I propose trying to address the notion of binder from a somewhat syntax-independent perspective. So let's just start work away from this informal definition with a binder being simply a mechanism that puts together some notions of terms with some notions of variables, no questions asked, but in a specific way. For example, this lambda binder just binds one variable in one term. This let binder involves two terms and one variable, but binds the variable only in the second. This more complex mutual let rec binder bind simultaneously several variables in several terms in a certain binding topology.
Well, so how about modular binder as a multivariate operator on sets together with a binding dispatcher theta, which says what bounds in what. So every element of f applied to sets of variables and terms can be seen as a container where the binding happens according to theta.
I see. So in our examples, for the lambda binder, we would simply have product, and theta will bind the only variable component into the term component, to the only term component. For this simple let, we'll similarly have products, but we'll make sure that the binding dispatcher theta indicates that only the second term component is bound, so we'll use two term components. Whereas in this let rec, in this mutual let rec, we will again consider only one term component and one variable component because everything binds everywhere in this particular case. But we'll have this more complex binding topology where we plug in the list type constructor and the product type constructor as well.
Yeah, exactly.
Okay, so this proposal is nice. This is very general, but it feels a bit vacuous. It is a little bit like saying, well, it's quite general because this arbitrary operator on sets can combine arbitrary shapes like lists and bags and trees and whatnot. But it's a bit vacuous in the sense it's a bit like saying that a binder is a thing, which is true and is very general. But how does it help us? We need a workable version of binder where we could, in principle, construct concrete terms.
Yeah, so the first thing I would propose is to make explicit the container-like intuition. So we assume operators that from any container can collect the content of variables and terms. Then, since we are modeling syntax, we would ask from these containers to store just a finite amount of content.
Hold on. We should perhaps we should not rush into assuming finiteness unless we really have to, because we want to model things like dome trees in lambda calculus or infinitely branching terms. So instead, we could probably develop the theory with just assuming boundedness by a fixed cardinal. So we assume that our containers will hold a bounded amount of content.
Yes. Then I guess we should assume functoriality. Namely, we will be able to rename the content component-wise in one container according to functions.
Okay, it makes sense, but I see two problems with this. One problem is that often when we are dealing with complex simultaneous binders, we want to avoid repetitions. For example, in this mutual letrec binder, we don't want to allow the same variable v on the left-hand side of both equalities. But unfortunately, the type constructor that we chose allows for that. So list of pairs allows for that.
Well, you're right. So let's introduce a linearization operator, which works on selected component. So for example, here, lists of v times t linearized at v, elements of this type are a list of pairs, and the first component of these pairs are all non-repetitive.
Okay, but this brings me to the problem, because this will no longer be a functor. When you are start with a linear structure and apply a function component-wise, you will introduce repetitions.
So I guess we should restrict our functoriality and ask for the variable argument functoriality only with regards to injections.
Okay. But so a second problem here would be the fact that so far we have considered binding variables, but we have completely ignored free variables. If we don't inject free variables, there's no variables to bind in the first place. And also some binding constructors put together, perhaps in complex combinations, both free and binding variables. This is a simple case. Let's say this PyCalculus prefix, where we have a free input, a free channel name, and a bound channel name.
Okay. So I guess we need a separate component here for free variable, and it has to be distinguished from that is marked in blue, and will be separate and distinguished from the binding variable component, since the role variables are playing binding or free are different. In particular, here we will ask full. It's no problem here to ask full functionality on free variable, because they can be repetitive in a term.
Okay, so you mentioned containers. Quick parenthesis here. There are several notions of container-like functors in the literature, and all of them are actually functorial not only with respect to functions, but also with respect to relations. So let's consider a unary case of a container for a second. If we imagine this as a container, an element of the functor is a container filled with content, and the functions are applied component-wise by the mapper, then we also have a relator that lifts the relations component-wise.
Relator will indeed turn out to be important. By the way, we picked bounded natural functors as our container-like structure for our work. Those are used for standard data types in Isabelle.
Okay, so let me summarize what we have so far. We have something quite simple. We have a multivariate operator on set that distinguishes between the free variable components, binding variable components, and term components, whatever terms are. It's required to be a functor with some properties where we restrict the functoriality with respect to injections on the binding variable component only, together with a binding dispatcher that connects the binding variable components and the term components. Is this right?
Yes, it's about right. Wait, okay.
Oh, okay, what have you done?
I just added some cardinality restriction. So
okay.
on here we assume functionality only with regard to small support functions, means functions that are allowed to change just an amount of components no greater than our fixed bound.
Okay, I will not ask you about this minor change. It's all in the paper, so let's move on. We could notice that so far our notional binder is independent of syntax independent in a way. So it just binds, as I said, any variables, any terms, no questions asked. But we actually want to constrict concrete terms, right?
Yes, and we can do this by simply here recursing on the hypothetical term occurrences, and so we get mutual recursive defined terms.
Okay.
Concrete terms.
All right.
Yes, here note that we keep separate the role for free, blue is free, and binding variable.
Okay, so I see why you want to distinguish between these two different roles, the free role and the binding role, but still I don't see how you treat terms specially so far. We just have raw terms, and in particular, we haven't used the binding dispatcher at all.
Of course. We have two quotient here by the notion of alpha-equivalence induced by theta, exactly the binding dispatcher.
I see. So you can define alpha-equivalence for an arbitrary functor.
Yes, and it is done by delving in the structure of the two terms. And here alpha-equivalence is equality on the free variables it allows renaming, bijective renaming on the binding variables, and factors see the renaming in the recursive occurrences of terms.
Okay, so you use the relator structure to lift this definition, inductive definition of alpha, which is quite nice that it's possible abstractly, but still it's very low level. It's very set theoretical. So the raw terms are an initial algebra. They are a fixed point of a given operator, but the concrete terms are just a quotient, which is...
Wait, hold on. Okay, definition does not count that much if we have an abstract characterization, and we have this theorem that characterizes our quotient terms as an initial algebra or with this operator, and this is an initial object on a equational theory, in particular Horn theory, with natural properties of terms.
Okay, and what does this buy us concretely?
With every initiality principle comes a recursor. Our recursor is careful to generalize the peak of art of nominal recursors, and we can define many useful functions from that, from these. In particular, capture avoiding substitution.
Okay, so we can completely forget about alpha equivalence and focus on this abstract characterization. So let's reflect this in our notation. So we'll just add a theta. We define these alpha equated terms as an abstractly by adding a theta as the fixed point equation. And I assume you have a similarly high-level induction principle, reasoning principle.
Yes, indeed. And also, thanks to our framework, we can play the dual role, and we will obtain coinductively binding-aware data types with a co-recursor and co-induction.
Okay, so and we assume the alpha equivalence will be defined co-inductively. So let me summarize what we have. We have this class of map-restricted bounded natural functors, or MRBNFs, or Mr. BNFs, if you want. They include the standard type constructors. They also have non-free type constructors that we can plug in, like finite sets, bags, even things that are not typically considered syntax, like probability distributions. And they are closed under the standard fixed point definitions. And more importantly, they are closed under binding relevant operators, such as linearization operator, and also binding aware least and greatest fixed points, which come with these side effects, this definition and reasoning principles, these high-level definition and reasoning principles.
Yeah, which means that we can define complex binders in a modular way.
Okay, give me an example if we still have time.
Yeah. So
the question. Okay.
Yeah, there's plenty of. So, let's
consider this syntax, this fragment of the Popelmark syntax. We have the types. We don't care how they look like. I hope our framework would work without knowing how the types look like, just assuming that they export some notion of free variables. We have patterns that are either variables or recursively. They are records of patterns where we use labels for fields. And the terms, this is a selection of the syntax for terms. Let's say they can be a term variable or a type abstraction or a pattern. And we assume, of course, that patterns have pairwise distinct variables. Well, so how would you handle this?
Yeah, I will start. We'll define patterns first of all as a standard data type, linearized at X. Here, FIMP-func is the MRBNF of finite partial functions. Then I will plug this to construct a binding-aware fixed point of terms, and note that pattern here exports both two different types of variable. A is for the Popelmark types, X is for the Popelmark terms, but note also that only the latter is bound in the recursive components. All the terms are bound.
Okay, so but how does this concretely look? So who's theta and who's f in this case?
Yes, please. And this is the formal definition. Again, note that there are duplicated occurrences for free and binding variables. This is needed because of the different role, and here they play both free and binding role.
Okay, that's it from our side. Are we the first to apply category theory to syntax with bindings? Well, of course not. In fact, starting from 1999, where there was a high density of papers in the topic, essentially the seminal papers on two main approaches, the nameless approach of de Bruijn and the nameful approach that was popularized by nominal logic. What we were the first to do is conceptualize binders abstractly as a first-class citizen and show that they can be used for alpha-equality terms and for modular reasoning and so on. Very quickly, this map shows our bounded natural functors and our variation for syntax with bindings in the context of some better-known classes of functors. They are just a particular case of accessible functors that preserves pullbacks, and it's suitable for higher-order logic. In contrast, type theory researchers tend to prefer the de Bruijn approach, the nameless approach, and they model this using things like index containers. Generality here grows bottom-up of the concept used. A final word about our competitors in the Isabelle ecosystem. They're also an important source of inspiration for us. The Isabelle Nominal 2 package that does some great things and also captured complex binders, but we are going to produce something even better. Thank you.
Thanks.
Okay, thank you for this very lively talk. So we have time for questions. Just raise your hand.
Have you tried, as an example, dependently typed syntax?
Yeah, so we're not very good at dependently typed syntax and this well-scopeness because of the underlying logic. So we haven't looked too deep into this. And also dependently typed syntax works very well with the de Bruijn representation. So there it meshes really nice in these categorical approaches. We take this nominal approach, which has other pros and cons. We give a 4-page survey in our paper. I think you can shout it.
Yeah. What's the time complexity for your system to process a data type definition?
Oh, it depends on the size of the data type. It can, well, obviously, yes. So I think, so probably just one can answer better this. So do you know that?
So for BNFs, not the Mr. BNFs, actually it's pretty good shape because the approach is modular, it's functorial, right? So compared with the old approach, which was very slow, that you had nesting, right? You have list of, and did recursion to that, it would explode, and there was formalization that took 15 minutes to compile and report it or stuff. It went down to 10 minutes, most of which was not actually data type constructions. I think because it's functorial, it actually scales quite well.
Yeah. One of the things where we improve is modularity. It's true.
So we still have time for some questions. So maybe you have one. How is it dependent from using Isabelle? Can you use other proof assistant to formalize the work? Or?
Yes, you can use it in principle, yes. You may have to assume the classical axiom, classical logic axiom, but yes, in principle, it works in other formalism. It works in particular in set theory as well, so anything that is based on set theory. This is higher order logic is a very weak set theory. So, yeah. We haven't looked at how it would work in a purely constructive setting, though.
One last question.
This one is for you.
The relators thing that you mentioned in the beginning, I guess they look a bit like logical relations. Have you worked out the similarity?
Oh, yeah. Okay, let me take this. Yeah,
because I actually, my problem is that I am not familiar with the logical relations terminology, but I guess yes. Andre knows
the
better.
relators are for logical relations. So they are for
Exactly.
listing relations. Here we assume strictly positive things. So if we factor in the function space, you no longer get a relator, you get a sub-relator. So it only subcommutes with relation composition. But yeah, I mean, the relator structure, we have this in Isabelle, we actually have this mechanism for transporting definitions across isomorphisms and more general things. So the transfer package. And this works with generalized relator. relators, which are essentially modeling logical relations, arbitrary logical relations. Well, it depends what we want to do with this, but this helps. We would have to formalize logical relation arguments, obviously, but we have the infrastructure to formalize this seamlessly, yes.
So let's thank the speaker again.
Thank you.